Hello, everyone. Today, we will discuss how subroutines are placed in procedures in assembly language. Here are the topics we will cover. First, how stack operations work, including using the stack to preserve register values and to pass parameters. Second, how procedures are defined using specific syntax. Third, the call to a procedure. Fourth, what to do when procedures are in an external library. Fifth, what a stack frame is and how it is used. Sixth, how to perform recursion. And finally, we'll look at INVOKE, a powerful procedure tool available in 32-bit x86 assemblers. Let's begin with how stack operations work. What is the stack? The stack in assembly language is a LIFO, or last in, first out memory structure. It is used for saving temporary data like register values, passing parameters to functions, and storing return addresses. On x86 architectures, the stack grows downward in memory, from higher addresses to lower addresses. The main stack instructions are push, which pushes a value onto the stack, pop, which removes a value from the stack, call, which pushes the return address onto the stack and then jumps to a procedure, RET, which pops the return address from the stack and jumps back to it. First, let's see how to use the stack to preserve register values. Before calling a subroutine, it is good practice to save the current values of any registers that the subroutine might use. For example, push EAX saves the value of EAX. Push EBX prime saves the value of EBX. Then, inside the subroutine, you can use these registers. For example, OVEAX, 10, OVEBX, 20. After the subroutine is done, you restore the original values. Pop EBX restores the original EBX. Pop EAX restores the original EAX. This is important so that the subroutine does not overwrite values that the main program still needs. Next, using the stack to pass parameters. You can pass arguments to a procedure by pushing them onto the stack. This is especially common in 32-bit assembly. For example, to pass the values 5 and 3 as arguments, you would push them in reverse order. Push 3, push 5, call add numbers. Inside the subroutine, these values are accessed relative to the EBP or base pointer once a stack frame has been set up. How does this work in memory? Each push instruction decreases the ESP or stack pointer and stores the value at the new memory address. Each pop instruction increases the ESP and loads the value from the top of the stack back into the target register. Let's look at a quick demo of stack operations. I'm OVEAX, 7, MOVEBX, 2, push EAX, push EBX is. Now, if we pop the values into different registers, pop ECX will load the last push value, which is 2, into ECX. Pop EDX will load the next value, which is 7, into EDX. So ECX will be 2, and EDX will be 7. Now, let's discuss how procedures are defined using specific syntax. What is a procedure? A procedure, also known as a subroutine or a function, is a reusable block of code that performs a specific task. It can be called from multiple places in a program. In assembly language, procedures are defined with labels and use the call and RET instructions. The syntax for defining a procedure is simple. You have a label that marks the start of the procedure, followed by the procedure's body, and it must end with a RET instruction. For example, my procedure, some code here, RET. The RET instruction tells the CPU to go back to the instruction that came right after the call. Here is a basic example. In our main code, we would have call greet, and then we would define the greet procedure, greet, some instructions to print a greeting, RET, a few notes on procedures. They do not require arguments, but they can receive them through registers or the stack. They must end with a RET instruction, otherwise the program will likely crash. You can define multiple procedures in the same assembly file. Next, the call to a procedure. What does the call instruction do? The call instruction does two things. First, it pushes the return address, which is the address of the next instruction, onto the stack. Second, it jumps to the specified procedure label. This allows the program to know where to return to once the procedure is finished. The RET instruction complements the call. It pops the return address from the stack and jumps back to that address. Together, call and RET control the flow of the program into and out of subroutines. For example, you can call the same procedure multiple times. Call say hello. Call say hello. Each time, the procedure will execute and then return to the correct spot right after the call instruction. This is because each call pushes its own return address onto the stack. Now, what to do when procedures are in an external library? What is an external procedure? An external procedure is one that is defined outside of your current assembly file. It's usually in another object file, a DLL file on Windows, or an SO file on Linux. You link to it during the compilation process. Examples include C standard library functions like printf. To use an external procedure in NASM on Linux, you first need to declare it using the extern directive. For example, extern printf. Then, during the linking phase, you need to link against the appropriate library, like the C library. Here is a minimal example that uses the C function printf. In the data section, we define a message msgdb hello from printf0. In the text section, we first declare extern printf prime. Then, in our code, movrdi, msg. This is the first argument to printf. xorrax, rax prime. We clear the rax register because printf is a variadic function. Call printf flat. To compile and link this, you would first use NASM to create the object file, and then use GCC to link the object file with the C runtime library. In summary, to use an external procedure, you use the extern directive to declare it, and then you link your program with the library that contains it. Next, let's talk about stack frames. What is a stack frame and how is it used? What is a stack frame? A stack frame is a structured section of memory on the call stack that is allocated every time a procedure is called. It acts as a container for the return address, function arguments passed on the stack, saved register values, and local variables. Each function gets its own stack frame, which keeps its execution context separate from other functions. Why use stack frames? Without them, it would be difficult to manage nested function calls or recursion. Stack frames provide organization and predictability. The anatomy of a stack frame typically looks like this on the stack, which grows from high memory to low memory. At the top, you have local variables, then arguments, then the saved EBP of the previous frame, and then the return address. To create and use a stack frame, you have a prologue and an epilogue. The prologue sets up the frame. Push EBP saves the caller's base pointer. MOVEBP, ESP sets the new base pointer to the current stack top. SUBESP, N reserves space for local variables where N is the number of bytes. To access data within the frame, you use the EBP register as a stable reference point. Arguments are at positive offsets from EBP, like square bracket EBP plus 8 square bracket, and local variables are at negative offsets, like square bracket EBP minus 4 square bracket. The epilogue restores the previous state and returns. MOVESP, EBP restores the stack pointer. Pop EBP restores the caller's base pointer. REach returns to the caller. Here is a full example of a function that adds 2 arguments passed on the stack. In the main code, we push the arguments and call the function. Push 3, push 5, call add. Add ESP, 8. This cleans up the stack after the call. The add procedure would look like this. Push EBP, MOVEBP, ESP, MOVEAX, square bracket, EBP plus 8 square bracket. This gets the first argument. Add EAX, square bracket, EBP plus 12 square bracket. This adds the second argument. Pup EBP RET. The key takeaway is that EBP provides a stable reference point for accessing data on the stack, which is essential for clean function calls. Now let's discuss performing recursion. What is recursion? Recursion is when a function calls itself to solve a smaller part of a problem until a base condition is met. Assembly language supports recursion by using the call stack and stack frames to manage the context of each recursive call. Each recursive call pushes a new return address and creates its own stack frame for its arguments and local state. The stack grows deeper with each call and then shrinks as the calls return. A recursive function in assembly will have a structure like this. It starts with the standard procedure prologue to set up the stack frame. Then it has a check for a base case. If the base case is met, it returns a value. If not, it makes a recursive call to itself with a modified argument. Finally, it has the standard epilogue to clean up the stack frame and return. Let's look at an example of a recursive factorial function. The factorial procedure would first check if the input value in EAX is 1. If it is, that's a base case, and it returns 1. If not, it saves the current value of EAX, decrements it, and then calls factorial again. When the recursive call returns, it multiplies the result by the saved value of EAX. It is critical to manage the stack carefully in recursive assembly programs. You must always preserve registers and maintain clean stack frames. And most importantly, you must have a base case to stop the recursion, otherwise you will get a stack overflow. Finally, let's look at INVOKE, a powerful procedure tool in 32-bit x86 assemblers. What is INVOKE? INVOKE is a high-level, macro-like directive available in some assemblers like MASM and TASM. It simplifies the process of calling procedures with arguments. It automatically handles pushing the arguments in the correct order, calling the procedure, and cleaning up the stack. Note that INVOKE is not available in NASM or GAS. The syntax is invoke procedure name, arg1, arg2. This is much cleaner than manually pushing each argument and then calling the procedure. For example, in MASM, you could write invoke message box A null offset milk text offset milk title MB underscore OK blank. This is equivalent to pushing all 4 arguments onto the stack in reverse order and then calling message box A. The benefits of INVOKE are that it handles argument ordering automatically, it improves readability, and it is less error prone. However, it is only available in high-level assemblers like MASM and is not portable to NASM or Linux environments. It also requires you to declare prototypes for the procedures. In summary, INVOKE makes procedure calls look more like they do in high-level languages and is best used in Windows programming with MASM. Let's have a quick summary of this entire section. We learned how stack operations work, using push and pop to save registers and pass parameters, we saw that procedures are defined with labels and must end with a RET instruction. The call instruction is used to jump to a procedure, and RET returns control to the caller. To use procedures from an external library, you declare them with extern and link with that library. A stack frame is used to organize a procedure's data, and it is essential for recursion and nested calls. Recursion is when a function calls itself, and it relies heavily on the stack. And finally, INVOKE is a powerful directive in MASM for simplifying procedure calls. This concludes our lesson on how subroutines are placed in procedures. Thank you.